Seventh grade. For math today, we have investigation number 7. If you are with me the whole time, you will walk away having completed your math assignment for today. But first, let's make sure we write our name at the top of our sheet here. Your name is not my name. Please don't write my name. Write your name. Okay, let's read. I'm on page 467. Make sure you're there as well. If you need to pause, do that now and get that math book open. It says, a cereal company claims on its box, 1 in 3 win a free movie pass. If you decide to purchase this cereal, what is the probability it contains a movie pass? The cereal box indicates that the probability of selecting a winner is 1/3. This theoretical probability means that out of all the cereal boxes produced for the contest, 1/3 contain a free pass. Thus, on average, 1 in 3 boxes is a winner. The very first note I want you to write down, guys, is the idea of theoretical probability. Theoretical probability is probability based on logic. If I were to have a coin, something like a quarter, theoretical probability tells me if I take that quarter and I flip it, I'm going to end up with either heads or tails. This is the one we used to talk about science a couple days ago of male and female. But if I have a coin, right, I have 2 possible outcomes. Right, and only one of them is going to be favorable. I really hope that I get the male side of this coin. Oh, I didn't get it. I didn't get what I wanted, right? So that's theoretical probability. Another idea we're going to come across, and I'd like you to write it down, is experimental probability. Experimental probability is probability based on experiment, or based on actually carrying out the process. Theoretical probability is based on logic. Experimental probability is based on the process. So let's see what we mean as we continue in our textbooks. Back to page 476. Does this mean that if you buy 3 boxes, you are guaranteed a winner? We can simulate the purchase of 3 boxes to determine the probability of buying at least one winner. For the simulation, you will need a spinner that looks like this. Each spin will represent the purchase of 1 cereal box. The probability of landing on a winner is 1/3, since the winning region fills 1/3 of the circle. Okay, now we're getting into activity number 1. For activity number 1, it says, construct the face of a spinner with the one shown above. Use a compass to draw the circle. The central angle is awesome. Use a protractor, all this stuff. It's going to explain to you how you can make a spinner like that. Guys, we have a spinner set up. We don't need that. But now I'm jumping down a little bit. It says to keep track of our results, we make and use a table that looks like this. Make rows for at least 6 trials on the table. So guys, we are going to create that table. Let's do it over here. Now along the top, we need 1, 2, 3, 4 columns. This one's a little bit bigger. Okay, here we go. So we've got spin 1, spin 2, spin 3, and we've got at least one question mark. Make sure you have this table set up. Now I'm going to make 6 rows for the trials. So let's see. Cut this in half. I'm going to divide this and this into 3s. Just like that. If you want to use a ruler to make straight lines, spectacular. If not, certainly don't worry about it. It's not a big issue. So what I'm going to put over here is trial number 1, trial number 2, trial number 3, trial number 4, trial number 5, trial number 6. And now, guys, what we're going to do is we're going to carry out this simulation. We're not going to buy the cereal boxes. We're going to use a spinner to simulate buying 3 boxes. So as I go, guys, I want you to fill out the answers, what we got for each of these spins. All right, here we go. Let's pull out that spinner now. So here's our spinner. This is trial number 1. The first spin we got not a winner. So if I bounce back here quick, I put N for not a winner. Let's go back and fill out the rest of this trial. Oh, now we've got winner for spin number 2. Oops. Spin number 3. We've got winner again. Now we've got this, not a winner, winner, winner. Now let's go do trials number 2, 3, 4, 5, and 6. We're just going to fly through here. Let's do it. Not a winner. So trial 2, spin 1, not a winner. 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 Now we're on to trial 3. Not a winner. Not a winner. Not a winner. Ouch. Trial 4. Winner. Winner. Not a winner. Trial 5. Not a winner. Not a winner. Not a winner. Ouch again. Trial 6, last trial that we're going to do. Winner. Come on, we need winner, winner, winner. Oh, not a winner. One more, last one. Not a winner. Okay, so now let's take a look at what we got here. If you didn't catch all of those results, I would like you to pause the video and write down all of these not a winners or winners here. Moving on, I'm going to fill out this at least one winner. Well, trial 1 had at least one winner, so I'm going to put yes there. Trial 2, not a winner, winner, winner. Yes, again. Trial 3, no. Trial 4, yes, there was at least one winner. There's actually 2. Trial 5, no. Trial 6, yes, there was one winner in trial 6. Okay, I'm bumping to page 477 and reading on. Simulation. For each trial, simulate the purchase of 3 cereal boxes by spinning the spinner 3 times. For each spin, record W for winner or N for not a winner. Then, in the at least one winner column, write yes or no, depending on whether there are any winners in the 3 spin trial. We just did that, right, guys? Number 2. Repeat step 1 until the table is complete. Below are some sample results. Okay, we already did that. Number 3, to compute the experimental probability of having at least one winner after purchasing 3 cereal boxes, add the number of successes, yes, in the last column, and divide by the total number of trials. For our sample results above, this would be 2/3. Okay, so if we're going to do that, let's do it over here. If we're going to do that, we have to figure out, well, okay, 1, 2, 3, 4, 5, 6. 6 is my denominator. And then how many were yeses? 1, 2, 3, 4. 4 out of 6, which is the same as 2/3. 2/3 success rate here. Okay, now let's get to our questions. Give yourself a little squiggly line to divide. This is kind of the experiment part. Now we're going to answer some questions. Question number 1. With one spin of the spinner, what did one spin of the spinner represent? Well, one spin of that spinner represented buying one cereal box. Number 2, what did each 3-spin trial represent? Well, if one spin represented buying one cereal box, one 3-spin trial, like we did up here, represented buying how many cereal boxes? 3 cereal boxes. Don't know why I'm putting periods here. It doesn't have to be a full sentence. Here we go. 3. What did the spinner stopping on winner represent? Ooh, up here when we got winner, what was that supposed to represent? That winner represents that we bought a cereal box with a movie pass in it. We got winner, that means whew, that cereal box had a movie ticket in it, right? Awesome. 4, what did the spinner stopping on not a winner represent? Ooh, if it stopped on not a winner, there was no movie pass in the box. All right, I'm moving on to number 5. Guys, we have 3 questions left. Thanks for sticking with me. Number 5 says, state whether the following tools could have been used instead of a spinner to conduct the simulation. Explain why or why not. So I've got 5. A, could I use 2 red cards and 1 black card to create this simulation? So instead of making that spinner that we had, could I use playing cards? Well, yes. Because 1/3 of the cards that they mentioned, right? They said 2 red cards and 1 black card. I can say, yes, 1/3 of the cards are black. B, could I use a coin? Could I use a coin to simulate a 3-box purchase? Cereal boxes. Could I? No, I could not, because I can't simulate 1/3 with 2 sides. Because there's only 2 sides on the coin, I can't get close to the idea of 1/3, can I? C says 3 red marbles. If I had 3 red marbles, could I simulate buying 3 cereal boxes? Well, I have 3 sections, that's good. But really the answer is no, because they are all the same color. I suppose if I were to take a Sharpie marker and color on one of those marbles, then yes, I would have 1 out of 3 that is a winner, right? So that would work. But if it's just red marbles, all the same color, no, I cannot. Let's go to D. For D, could I use 1 red, 1 white, and 1 blue marble? Well, yes, I could. I would have to designate which color is the winner. All right, let's take a look at E. E says, could I use a number cube? Ooh, a number cube has 6 sides. Could I use a number cube or a die to do this simulation. 6 sides, 2, 3, 6, those numbers kind of work together, don't they? In reality, yes, I could. I would have to, again, designate 2 numbers now that are winners. That's a quotation mark. It doesn't look very good, but that's what it is, okay? You can trust me. All right, let's take a look at number 6. Number 6 says we use simulation when the theoretical probability is difficult to compute and the experimental probability is impractical to find directly. In this case, why is it desirable to simulate the experiment rather than actually perform the experiment of purchasing cereal boxes? So guys, if I'm going to carry out and I want to study the probability of getting a movie ticket from a cereal box, why would I do it with a table and a spinner instead of actually going out and buying a whole bunch of cereal boxes? What we did here is we basically simulated the purchase of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 cereal boxes. Well, why would I rather use a table and not go buy 18 cereal boxes? Well, I don't want to buy the cereal boxes because that's going to be pretty expensive. It would also be, in reality, pretty wasteful. It would also take more time. Right? So I'm not going to actually buy 18 cereal boxes to do the experiment because of all these reasons. So that's your answer for number 6. Let's go to number 7 and end our class today. Number 7, I'm on page 478. Assuming a large number of cereal boxes were made for this contest, one can use probability theory, not simulation, to show the theoretical probability of having at least one winner after purchasing 3 cereal boxes is 19/27, or about 0.704. What is the difference between the theoretical probability and the experimental probability you found? Why is it important to conduct many trials computing an experimental probability? Okay, so theoretical probability for this scenario was 1/3. 1 in 3 boxes is a winner. What we found, our experimental probability, was 2/3. Let me state that again. Let's see, we've got 18 boxes. So that's our 18 boxes is our possible outcome, right? Let's see how many winners we had. Let's go past just the trials and take a look at the spins. How many winners do I have? I have 1, 2, 3, 4, 5, 6, 7. I have 7 winners. 7 out of 18 were winners. So the difference here isn't very much, right? 1/3 and 7/18, because really 1/3 is equal to 6/18. The difference, make sure you write it down, please. The difference is 1/18. Okay, let's make sure we answered number 7 totally. What is the difference between the theoretical probability and the experimental probability you found? We did that. Why is it important to conduct many trials when computing an experimental probability? Guys, I use many trials to get a true read on things. You know what I could have done? I could have just done one trial and found out, you know what? In this one trial, if I just look at that one trial and nothing else, I got two movie passes when I bought 3 cereal boxes. So that would come out to be 2/3, which would be way off of what we actually got, even in our experimental probability. The more experimenting I do, in reality, the closer I'm going to get to theoretical probability. 7th grade, that's as far as we are going today. Thank you so much for your hard work. Thanks for putting it in today. Thanks for following along with me. Your assignment is easy. You took the notes. You turned the notes in. Your name's already at the top. You turn it in, you got an easy peasy A. All right, make sure you turn that in. And thank you for your time. God bless you. Have a great, great weekend. Bye-bye.